Good morning, everybody. Just a little quick about me. I got introduced to Clojure about 10 years ago, but my first exposure to Lisp and functional programming was back in 1995, so as you saw how old I am. And I've really been kind of, been two kind of paths in my career. One is functional programming, and the other is distributed systems or systems in general, and this is kind of a combination of both of those things. So, had a career in a variety of industries, most recently in fintech, and this is what I'm talking about today. And thankfully I'm not that far away, so I just drove over here. So I work at Splash Financial. We're essentially a middleman between lenders and borrowers, and basically in three different areas: student loans, personal loans, and most recently in home equity lines of credit. We're a relatively small company, about 40 developers, and about 150 people total. So what are we doing at Splash, really? Like, what's really the problem? So I think one of the key aspects of this that makes it different than a lot of other things I've been in before is there are very high consequences to getting it wrong. You make a loan for $500,000 to the wrong person, that has a big deal. So we don't have that much high throughput, but there's a lot of risk involved, and most of the data we deal with is highly sensitive. So being very careful with that data is very important. And part of getting it right is having reliability and correctness in terms of the computations you do, and also auditability of what possibly went wrong, if it did went wrong, and knowing how to correct it. And then the last big challenge is that there's a constantly evolving market out there, and we need to be able to try new experiments about how to have different behaviors in the learning process and be able to do it in a way which is safe and doesn't break things that already work. And so that drives a lot of the design behind this. So to save a lot of time, I'm going to assume that you basically agree with this. I know that there's a lot of gray area in some of these things, but with 30 minutes, I don't really have enough time to get into all of this. But just to say that FHIR is very much on the good side of this. And it's a variety of event sourcing in CQRS. I'd say it's a kind of evolution of that in my mind. This is my, I think, fourth time kind of getting into this area, but for those of you maybe not as initiated as much into all this, just a quick primer. Event sourcing is the idea you have a set of facts from the world, you have some sort of computation that updates a kind of aggregate state. You can think of this as basically just reduce in Clojure. You carry your state along, and that state is completely derived from the combination of your input facts and pure functions, right? Which is nice because you can change your pure functions and reevaluate. You have a full history of everything that's ever happened. Has a lot of strengths. And simply, I could get into a lot of details about this, but CQRS is basically the idea that you want to separate the part that deals with incoming novelty and doing that kind of computation I was just talking about from the part where you're trying to query or look at different combinations of your data and have those in different subsystems, often connected by events or Kafka or something like that. And FHIR has this kind of architecture as well. Okay, so what are drawbacks of this, or things that maybe motivated FHIR to try to go beyond that basic formulation? So the first one is that when you have one of these kind of processes like this, you end up having to pack a lot in these green boxes at the top. And oftentimes that leads to FSM or like state machine-y kind of mechanisms. And you get to a place where that becomes overly complex and hard to reason about. You may have a variety of different input events. They're not all the same kinds of things, but you have to represent somehow this cumulative history and some sort of enums or things like this, and it can quickly get out of control. And what Splash does, there can be hundreds of these kind of like interactions of things. The other is that if oftentimes, not always, but oftentimes these systems tend to have a kind of streaming basis to them in which different aspects of the state are located in different deployed services. And this makes it difficult to understand, difficult to debug, and just difficult to operate to change. So it has a lot of strengths in terms of performance and scalability, but it has a lot of drawbacks too, that I think have made some people be cautious to get into. So how's FIRE different? So what is FIRE? This is just a acronym we came up with. We wanted to call it something like MNTAT, but the management didn't like that. So we had to come up with this. Turns out it's nice and slack because you can use a little fire emoji and things whenever something's deployed. Okay, but what is it really? So the number one thing is that those green boxes at top are no longer just like some map. They're actually a graph. So what's important here is that we represent a process as a set of these pure functions, but there are explicit steps between them. So we know, like, when new data is input and a series of computations have to happen, we know exactly which data flows through which steps. It's not just mysteriously because the functions happen to call each other. We have that codified as a data-centric thing. And the other thing is that this is a reactive process. So observations, I'm going to use some FIRE terminology here. My apologies if this overlaps with other people's words, which don't mean the same things, but I'll try to clarify. Observations for us are just straight ground truth facts, things you measure from the outside world. So this could come from our customers. This could come from our internal underwriters making decisions about things. It could also come from external data services like credit reporting or income reporting or other things like that, risk reporting of various kinds. And one of the important things about FIRE is that we've centralized all of the business logic, computations, and the event store in one service. So it is kind of a monolith in that sense. But our experience is that we can do graph evaluation in a matter of like hundreds of milliseconds, low hundreds of milliseconds mostly. We don't have scalability issues. We're not going to handle more than single-digit thousands of applications a day, not like hundreds of thousands a second or anything. So this works perfectly well, and our experiences probably could scale to very large numbers. But let me just show you a little example of what it looks like. So this is sort of the very high level of how FIRE works. It starts with an observation that comes in from the outside world. There's a graph evaluation. You can think of that observation as being the leaf on a tree, and then whatever's downstream of that leaf gets evaluated. And that collection of both the observation and any derived events that are created along the way, we store together in a transaction in a database. That kicks off a process. The response to that is we update a set of leaves that we would like to go acquire. So one of the kind of key ideas here is that imagine the loan process where the root of the tree, and this is tree theme for this year, is our decision about the application. So we either accept it or deny it, let's say in simple sense. But we could be in this intermediate state, which is we know something about the application, but we don't know enough to go either way yet. And so the trick is, what do we need to go gather from the outside world in order to make progress on that? And so the graph has this interesting characteristic. It is not just one way. Each node in the graph, in addition to returning value, also returns which of its inputs it would like to have fresher values on. And we kind of backwards trace that up to the leaves and use that to drive to ask the front end what to go do. Similarly, the observer services, which are kind of microservices that are responsible for interacting with some sort of data provider from the outside world, also are communicated through events called commands, which drive that kind of interaction. So it's kind of like a rinse and repeat sort of process. We get a new observation, we evaluate it. Did we get to some sort of conclusion? Okay, we're done. If we didn't get to some conclusion, what do we need to go farther? And then we just kind of keep going, right? So here's a little more detail. I hope this is readable at this distance. So you can imagine we start with this blue observation here. That causes some evaluation downstream of it in the tree. These green nodes we call inferences. And then all these things are committed as this transaction, as I was saying before. And then here's another example. We get a second observation. It creates another generation here, generation 2, so on and so forth. One of the really interesting aspects of FIRE, and in some ways I think it was sort of in our design, but I think in practice we realized it was much more powerful and useful than we thought at first, is that the evaluation of any of these nodes, which are just pure closure functions, basically, could potentially throw an exception. And you can use that exception throwing as a way to signal that the input of the observation is not what you want. So for instance, you could use it to say, the loan has gotten to a certain place where we don't want to accept any changes to your credit profile. And if you try to make more observations like that, we will just say, no, thank you. And that whole transaction will not be committed to the database. And it allows us to have, a lot of event sourcing systems have this characteristic of, they can't really control what comes in. It's just a whole pile of things come in and then they have to react to it. This allows us to say, beyond the normal validation kind of constraints of like, it's a malformed image event or we don't know what you're talking about, we also have, well, actually you picked a loan amount that's outside the range that we already said that you needed to pick, so we're not going to accept that, right? Okay, so going forward, this is sort of like high-level taxonomy of fire events. So we've talked about observations and inferences. There's actually a couple other flavors I won't talk about, but maybe any questions in the hallway. The other one we should really talk about is commands, though, and how we handle asynchronous and side effecty kinds of things, because we keep all side effects out of the graph. So when a graph evaluation happens, there's no external communication with the outside world, and the only real communication is just the state from the database and writing to the database at the end of the transaction. What commands allow us to do, and I'll show you an example here, is to capture the information necessary to go do a side effect. So in this case, we get this new observation, the blue one. Now, the function for a command is a little bit different than an inference in that it can decide not to produce an event. Inferences always produce something. It could be nil, but like commands basically can say, I don't want to do anything. Or they can produce a command event, and the command event's value is essentially the information that's going to be necessary for a handler to go do something with it, right? But like every other evaluation, we create another generation, it's put into our event store, we return back to the caller. By the way, that observation thing is a synchronous HTTP call. So you say, here's my new observation, and you get back that information about what new observations you might want in the future. Okay, so we also have Debezium kind of in this that takes these events off of, this is in Postgres, puts it into Kafka. And then we have these observer services, which are Kafka consumers, and they have handlers that look for specific kinds of events. So this could be like, say, our TransUnion credit reporting service, for instance. It goes and makes this any kind of external communication it needs to do, and then as a consequence, it makes an observation, and that restarts the process again. Right? Okay. So I'm going to show you an example of all this in just a second, but just a few things about the process. Last November, about this time, we started implementing this. This is the architecture and building a new product. We had a relatively small team. We managed to build a new product that we launched in the spring in about 7 months. It was remarkably more productive than our previous architectures. And since then, it's had great performance. It's had essentially no significant production incidents, very minor things. And it has a level of security which is very high compared to our previous things, which I'll maybe talk about at the end. So what I'd like to do now is show you an example of a tool we have called Hydrant that we use internally. And this is sort of like our extension to the IDE, you could say. So let me back up here for a second. Sorry, this is a little bit hard with the touchpad, but so zoom in a little bit. This is sort of the root of the tree of our HELOC application thing. So this is in our staging environment. This is the real thing. And we have these nodes at the top, which are kind of like the conclusion, right? And you can see that they have a bunch of different things that flow into it. And these orange lines are that kind of acquisition log, as I was talking about before. So essentially what it is saying is this taskmaster is saying, like, I still need you to do confirmed declarations and your employment stuff and deal with the offers. I don't need you to do these things up here that are black. So let's just follow a pathway all the way up to and see what it looks like, right? So I won't bore you with exactly everything along the way here. It's pretty involved. But eventually, we get to something like this, which is like, okay, well, we need your date of birth still, and we still need your phone number in order to go get the credit report. So this is the command node. You can see it hasn't been clicked yet. And if we look on something that we already have a value for here, fans of Portal might recognize this. So we can inspect the data for any of these nodes. We also have this other panel on the left, which shows us the history of all events that have happened. And this is the current generation that we're in. And if you scroll down here enough, you can see these black boxes are where events are occurring. And up here in the top, or these blue ones, are the observations. And down here you can see there's some of the inferences and finally commands. So let's go back and I'll show you what it really looks like as we make progress in this. So this is the actual application. That's what it looks like when you're, I've fast forwarded up to this point so we can get faster through it. But you can see that actually I'm providing 3 different kinds of information here, date of birth, phone number, and this consent. And in Fire, those are actually separate things. Zoom here a little bit. So there's the consent, there's the date of birth, there's the phone number. We have them separated so that the UI can reformulate these things at will without us having to worry about that. So we're very, very decoupled from the front end. Which I'll explain a little bit more in a second. But let's go ahead and do this. Oh, that's not good. Maybe just because we're the network's been a little janky here. Okay, sorry. That's why I saved this link. Hopefully this will get us back. Oh, man. All right, I might have to hand wave on this a bit. How much time do I have? Okay. Let me try to jump in real quick. So this is a little tool we have called Marshall that allows us to do like testing and stuff like that. And so I'm going to go ahead and create a new application here and try to speed run through this a bit. Let me hide some of this. We have this test user called Nancy Burkhead. Don't ask me why it's called that. I'm sure there's a real Nancy out there somewhere. I apologize. Wait a minute, I gotta grab some information here real quick. Always fun for the conference network here. Right. So we got that. Fill out some of this stuff. Full-time employed. Let's see. Okay, I think we're about back to where we were here. Okay, maybe easier for me to paste than screw it up on a, I don't know, typing on a laptop keyboard is just never a good experience for me. This can be anything, so we can. All right, so here's where we should have been a minute ago. And if we look back in here in Hydrant, oh, it's going to be a different user, so let me get that. So there's a little bit of the secret sauce here. This part of the URL is actually the GUID for the account. Kidding me here? Oh, man. Yeah, I'll just do that. All right, now I got to navigate back to it, though. Let's see, the quickest way, just start here, I think. All right. Okay, so we see we've created the command here. Let me jump in real quick. Look at that. And you can see it's kind of a collection of the information that from its inputs that were necessary to fulfill this. And that caused the transfusion service to go make this observation here. And this little dotted line is sort of saying, this is kind of like a leaf, really, this node I'm looking at. The dotted line means there was this asynchronous kind of pathway that was happening in between those things. And if we look in here, we got a bunch of details about the credit report and trade lines and all that kind of stuff, right? So if I open this up more, we'll see that we've filled out more of this graph. And if we go back to the application, I'll just pick some of these things and fast forward a little bit here. Let's say maybe 400,000. And so here's where we're actually offering the rates. So we've done all the pricing calculations. The first step in this is people put in what total amount of money they're going to draw, because they don't have to draw all of it at once. And then we figure out all the interest rates and all that kind of stuff. And we pre-compute all this in like a lookup table. So it's really fast from the front end. And you might even notice it's like changing interest rate as the amount of money, because we have different adjustments at different things like that. So there's a lot of computation that's happening in the back end to kind of support what's happening here that's in that graph. And if we pick one of these things, you know, we're getting farther into the process, and I can go back to Hydrant here and we can see kind of what's happened. One of the really nice things about this is it allows us to really inspect in detail every aspect of this, right? So I'm just gonna jump all the way here to the end so I can see this. But you'll see now, let me update, refresh. The confirmed offer is no longer being acquired. And so we have this very loose coupling between the front end and the back end. Basically, the back end says, here's the things I still want to know. And the front end decides, well, what order should I present those? And how should I group them? And how should I arrange that? And the back end doesn't know or even care about that. The order that the front end provides those observations could happen in any order. And the back end will process it just fine. It's written in such a way that it does. And that allows us to do fast iteration on the front end without having to have any real coordination with the back end. In fact, it was so ridiculously decoupled that I think at the time of launch, we had never actually run the front end and the back end together. Like the front end developers didn't need the back end developers didn't need the front end. We were just like kind of plowing ahead. More recently, about a month ago, we managed to get that all working, but it's funny that we didn't need it, you know, like it, whatever time I've got left here, let me see, quick time check. So there's a lot of, let me jump back to the slides for a second. So there's a ton of stuff I don't really have enough time to talk about, but I just want to mention them, right? We use Mali to define all the attributes, and we do it in a globally namespace way. We have not just the validation associated, but we have data classification. So we say how sensitive it is, and also documentation attached to that. And these attributes are used across all events. So when you see that attribute, you know what it is across all the events that are created. We have end-to-end envelope encryption of the data, of the payload of that. So whether it's sensitive or not, we protect it as if it was the holiest of holies. That happens in the database and in Kafka. We can do local development with Fire because we have pluggable modules for all the pieces of it. We use Integrant to put this all together. We can replace the Postgres database with an in-memory map, Atom kind of approach to things. And because of that, we can run the entire basically logic of our whole system in a test or in the REPL. Also, our whole thing is specified with like data specifications, the nodes and the graph structure and all that kind of stuff. So you can write a test like, instead of having 50 nodes, I want these 6 nodes. And I want to stub out the inferences for some of the leaves with some test observations, and I want to run that in my test and do a generative test on it. Allows us to do like very fast, very exhaustive, easy cycle. You really could disconnect your laptop from the internet and do development all day long without any problem. We have staging environments and stuff, but we don't really use them as much as we do local development. It's probably like 80% local development. It's also a great debugging tool, Hydrant. So the day we released it, on the first day, we had a bug. We found out what it was, I'm not joking, in 10 minutes. We jumped into the graph, Started following through the graph. Yeah, that looks right. That looks right. Okay, it all looks right. What's the front end doing? And it turned out it was a mistake in the front end. They got it kind of wedged in the state. But it was very easy to figure out where the piece of code was, where it was. I already talked about testing. Oh, this is a big thing. Probably I can barely talk about it, but like our code is immutable too. So when we release a node into production, the source code is in its own namespace, and we never touch that namespace again. The example we would touch that if it was broken. It doesn't work at all. But if it's in production, it's going to stay that way. If we need to make any changes, it's like we're making a new major release to a library. We treat it internally that way. This means that we know that any graph any application that's in production is using a specific version of the graph, and we know that it will continue to behave like that forever and can't be broken by any experiments or new approaches that we're doing. That allows us to have this kind of experimentation kind of for free. Like our whole backend infrastructure, you could say, is versioned. And so simultaneously, we can have multiple approaches to things going on. We can do A/B tests from the whole thing, not just of a whole feature, but like the features only, it's like the whole graph. Very interestingly, and this is one of the things I'm most proud of, we developed Hydrant very early in the process, like in the first month or so of development, and we used it throughout. We used it to develop these graphs with product. We would sit in a Zoom meeting and actually literally be building the graphs in Hydrant while talking through the problems with them. The nodes in these graphs represent business significant events. They're understandable to product and business people. They're not a mysterious black art that only the developers know. And then the last thing that we haven't really fully implemented to the degree that I would like is all that stream of Kafka events we can use to do projections. We can use to do things like inventory management, reporting, analytics. We already send all this data into Snowflake and use that for data warehouse stuff, but we have a lot more applications along the way that will be using the exhaust of that. And that's basically it. I just want to thank the people besides me who contributed to this, and there's quite a few. A lot of the people who were involved in the design were also involved in the implementation of it, but it was really a whole company effort. And we took quite a long time. I think this is a great example of how if you spend 7 months of time doing design, you can spend a month and a half doing the implementation, and it works really well. So that's it. Thank you.
Thank you, Jim. We do have a few minutes for questions. There's a mic up here if anyone wants to walk up and ask a question. Feel free to ask Jim all about fire architecture or another burning question on your mind.
So Hydrant looked brilliant. That was excellent. What's the basic tech behind the front end of what you're displaying?
It's ClojureScript. I think we use a TypeScript library to do some of the graph drawing, but Portal's embedded in it, you could say. Yeah, it's we just kind of designed it from scratch to meet the needs that we thought we would need in order to understand this stuff. I have to say, if you look at the namespace that defines the edge list for these graphs, it's like, about 2.5 pages long worth of, it's mind-numbing. Like without this, you would not be able to understand it well. I think this is almost like critical to have this kind of tools in order to do this kind of work.
Okay, we have time for one more question. Go ahead.
Thanks for the great talk. I'm wondering, you mentioned every node is versioned as you build up. Is there a way to decommission old versions or eventually clean up the code that is no longer used in production?
More theoretically than practically. We haven't had to yet because it's early days, but we have been thinking about that for sure. And I didn't really talk about it, but we have a lot of things built into our CI/CD system to ensure that you didn't break something too. So for instance, we generate a whole bunch of example applications, run them through the graph of a certain version, record those events, store them in S3, use them later to, when you produce new versions, to make sure no one messed with some function that was a dependency of something that changes behavior. It's not perfect, but it's also the way we've organized our code helps to make it easy that someone might make a breaking change, right? Each node has its own namespace. If you're editing that namespace and it's not like new, it's pretty clear you're doing something wrong to start with. So eventually, to more directly answer your question, we can do analysis on the events that are, the applications that are still in flight, what nodes are being used. we could figure out what nodes are no longer being used, mark them as deprecated, and eventually remove them from our code base. We could even offline events of our database and put them in cold storage and stuff like that, and have a backup to read from S3 or something like that, if we ever need to rehydrate them.
All right, one more round of applause for Jim Callahan.